Welcome everyone. I am a computer engineering student in my senior year, and for one of my final projects in a computer architecture class, I get the wonderful task of designing a CPU architecture and an ISA. Now, that is a bit of an undertaking, and I have quite a bit of time to complete it, but I decided that in preparation and in the process of coming up with and implementing this design, I'm going to use this game, Turing Complete, to walk me through the basics that I know to further understand them and into the more complicated parts. Now, if you don't know what this game is, Turing Complete is a game where you do just that. You go from the wires, the very basic logic gates, all the way to the uber complicated processors, right? And as the great Richard Feynman said, the ultimate test of your knowledge is your capacity to convey it to another. So, whether you are a student also looking to learn or just another person interested in how computers work, I hope this helps you understand it, and I hope it helps me understand it. So, let's find out how a computer really works. Alright, so I've played this game some before, but I never finished it. If we go to the campaign, oh, we'll get right into it. Congratulations, you've been abducted. We're testing you. The rules are simple. Build a functional computer or you will be eaten. Good luck. Dude's looking kind of funky. A signal flows from the input to the output. In the upper left corner, under input, there's a green icon. Click it to turn the input component off. All right, this is a wire, right? This is the foundation of transferring electricity, right? You give it power, it conducts power, right? Technically, well, yeah. I don't know why this box is appearing down here, but we're very impressed with how well you completed your last test. Okay. We've decided you're probably not a plant. I'm offended by the probably. This level, the challenge is to figure out how the NAND component works. Be sure to figure it out before you complete this level or you get stuck on the next level. All right, first, oh, I haven't unlocked the level map yet, but oh, this I was about to say, it looks like it's already built. So this is a NAND component, like they said. That just stands for not and. So when both inputs are on, you see it takes two inputs and it gives one output. When both inputs are off, it gives an on input, right? It's powered on. If I give it top input, still output's on. If I give it the bottom, still on. But if I give it both, it will turn off. Oh, so it is on in every case except this one, when they're both on. Correct, you've unlocked the NAND gate. With this component, you can build everything else in your computer. And that is true. This component, the NAND component, is what's known as a Turing Complete component, which means that any logic that can be synthesized, you can synthesize with only NAND gates, which is wild to think about, but we'll prove it. All right, as you unlock the NAND gate, it is time for you to build a circuit. Last level, you made the table that described the circuit. In this level, you will build the circuit that matches the table. So you see here, it will oh, use NAND gates, build the NOT gate. All right. So we want it, the NAND gate, this is its we call this a truth table, right? When input 1 and 2 are 0, we output 1, and so on and so forth. I don't know why that's blinking. So it wants us that when input is on, output will be false, and when input is off, the output will be true. Now, this is, oh, up here I have my components. Now, if from what we know about the NAND gate, for it to be off, both have to be true, right? And we want it to be off when this is on. So if we just pull a wire to here and to here, oh, I didn't mean to do that. Can I control Z? I can. We see that this is now meeting the second requirement, and if we turn it on, also meets the first, because that was also a case where if both are on, it will be off, and the inverse. Perfect. I've unlocked the map too. And the not component. See, the way this game does it is once you create a component like this, I have made the not gate, which just inverts what is input into it. But now I've unlocked the component, so it'll show up here. Okay, yeah, this is the level map I was talking about. I've got to, as you can see, we have a long way to go. I have gotten up to here, somewhere in here before. I think I was, yeah, I'd finished this one, and these two. So I got kind of far, but I did not get all the way up to the ISA, the final, that's the goal. So let's finish the rest of the basic logic section. So next are the three base gates. Well, there are four base gates. There's NAND, AND, OR, and NOR. Well, NOR and OR. So let's go to AND. Right now, the elephant is dominating all the other test subjects from Earth. Adjusting for brain size, you are also doing well. What is the smartest animal per volume? I don't actually know. I don't actually know what that is. All right. Create the circuit that matches the table. Double click on a component to move it connected with wires. All right. So we're trying to make an AND gate. So this is a NAND gate, which is the inverse of an AND gate, right? And what we want it to do, right? Because if we look at this thing up here, we'll notice that the output is inverted from what we want. So if we just take a normal NAND gate and then invert it, you have a standard AND gate. Beautiful. Also notice that for the NOR gate, most creatures on Earth are aggressive and cannot focus. To succeed, you must learn to think logically while not destroying things. And create a circuit that matches the table. Now for this one, we want it to only be, this is the NOR gate. It will only be on when neither of the inputs are on, which is, if we once again look at this logic table, does it show up if I do this? It does. Right. So this is the only case where we want it to be on. So if we do a little inverting of the inputs, right? You can now see that it's off. Well, it's not going all the way through. I mean, this isn't complete, but you'll notice that as you go through it, it's on, off, which is the inverse of what we're looking for. So all I do is add another NOT gate. And now you're starting to see why the NAND gate is Turing complete. Because remember, you can make a NOT gate out of just a NAND gate. So you can think of this, we can actually remake this with only NAND gates if we wanted. Just clean this up. Yeah, okay, it's not gonna look pretty, but that's fine. If we, oops. See, now you can see we can make a NOR gate out of only, where's my, oh, I clicked it too many times. It's fine. Now you see we can make a NOR gate out of only NAND gates. And as we move on to the last of the fundamental logic blocks, you'll see that, oh, You should be happy to get to participate in our glorious tests. I'm very happy. Get a chance to communicate with the very advanced people from the galactic civilization. Cool, create a circuit magic. Now the OR gate. This is very simple. If either of the inputs is on, right? If 1 or 2, then it outputs on. Now remember, I already said that a NAND gate where you invert the output is AND, and if you invert both the inputs and the outputs, you get a NOR. Well, now you can see quite that if you just invert, then or I'll make it just out of, I'll do it both ways. If you make it like this, that's giving us the right output at 0, 0. There we go. That is the OR gate. I'm not going to go forward just yet. I'm going to switch schematics. I'm going to make a new one. Open this up, and it'll prove that you can, once again, make it with just NAND gates. And note that NOR, the NOR gate, is also Turing Complete, just like the NAND one. Oh, oh no, this is right, yeah. Perfect. Now note that the NOR gate is also Turing Complete, but the AND and the NOT and the OR gates, sorry, are not Turing Complete unless you also have an AND gate, a NOT gate. I've confused myself. But those are the basic. I'll do one more, right? The always on. Create a circuit that is always on. You can see why that would be useful. Sometimes you need something to stay on. Well, I know that, right? Well, this will be an OR, right? Because I need to, if it's off or if it's on. So in the case that it is on, that's easy. If it's on, this will be on and that works. But if it's off, just invert this. It's on. Check that. There, it's off in all cases. This level unlocks your first manual page. This was important. Make sure you understand it. Yes, De Morgan's laws. This is what I was talking about. The truth tables of the 4 fundamental gates are symmetrical. You can convert between them by inverting the input. That's what going here to here is inverting the input, or inverting the output. It's from here to here or here to here, as indicated by the graph below. Get any basic gate to any other. At most, you have to NOT both inputs and output. Right? So NAND, if I invert the input, goes OR, and then if I also invert the output, I'm at NOR. You can do this for any of them to move around. You can go between OR/NOR by inverting output. Same goes for AND and NAND. In fact, NOR means not OR and NAND means not AND. Notice the component shape of OR and NOR are identical except for the little dot on the tip. Yeah, if you'll notice that, this tiny little dot right here is an implied inverter, right? Same one here. Because in the case of a NAND, it is a AND gate where the output is knotted. Same with NOR. Negating the output flips all the bits in the last row of the truth table. Negating the inputs mirror the last row of the truth table around the center. All right, so if you look here, it's on the right side. This mirrors it around the center, so it becomes here. Same thing from here to here. But if you want to go here to here, you're inverting them, which makes sense. All right. De Morgan's laws are huge for computers, right? If you're taking digital logic class, you need to know that. Learn De Morgan. Very useful. But obviously I've unlocked more components. On, off, and manual. Off is just the inverse of this. You can just, I guess I could make it, if instead I made this an AND gate. I don't know why you would want this, but this will always be off, as you can see. There, if I go to the level map. That is all of the basic Like these are the basics of computers, those four gates plus the inverter. From there, you can make the CPU that runs the computer that you're watching this on. And that's pretty cool.